Good morning.
Good morning.
There are many types of motion in the nature. In this lecture, we will study about the simple harmonic motion. In short form, we indicates it as S.H.M. S for simple, H for harmonic, M for motion. And the definition of simple harmonic motion is if a particle move to and fro in a straight line about a fixed point such that the force is directly proportional to the displacement and the force works against the displacement, then this type of motion is known as simple harmonic motion. It means it is clear from the definition of simple harmonic motion that there are two important points in the simple harmonic motion. First one is force is directly proportional to the displacement, and the second one is the force works against the displacement. It means if the body moves in this direction, then force works against the displacement. It means this direction about a fixed point. So now let us consider that a point O is a fixed point and the particles move to and fro. It goes A and then it returns at B, and about a fixed point O it moves A to B about a fixed point O. This is the simple definition of simple harmonic motion. And example of simple harmonic motion is the pendulum. The bob moves to and fro about a fixed point, and this is the example of simple harmonic motion. Now, let us consider that at any time the particle B at point P and its distance is from O, that is the middle point, is x. Then from the definition we have f is directly proportional to the x. This is the equation number first. This is the equation number first. Now we want to derive the equation of simple harmonic motion. The equation of simple harmonic motion, from the beginning we start that the force is directly proportional to the displacement, where F is applied force and x is the displacement. X is the displacement. Now we all know that when we remove the sign of proportionality, then it changes in equality and a constant term is multiplied. So we have f is equal to minus kx, where k is a proportionally constant known as a spring constant. A spring constant. Here negative sign here negative sign indicates that the force works against the displacement. This is the definition of simple harmonic motion. Here negative sign indicates that the force works against the displacement. Now we know that F is equal to mass into acceleration is equal to minus kx. Chunki F is equal to mass into acceleration, and A is equal to minus k by m into x. The acceleration is written in differential form as d2x upon dt square is equal to minus k by m x. This equation is indicated by A, where we will discuss about this equation. So here we write A. Now we proceed. Now we will proceed as this. Now the d2x, now the equation became d2x upon dt square plus k by mx is equal to 0. This is the equation. Let it is the equation. This equation is first. So equation first, it is known as differential equation of simple harmonic motion. It is known as differential equation of simple harmonic motion. Now we will discuss from equation A. At equation A, in equation A, in equation A, it is clear that the x is multiplied by some constant and having negative sign, then it is equal to its second derivative. This property is found in sine and cosine curve. So we can say that the trial solution of equation first is x is equal to a sin omega t plus alpha, where a and omega alpha are constant, where a, omega and alpha are constant. Now differentiating it with respect to t, we have dx by dt. Dx by dt is equal to a omega cos omega t plus alpha. A omega cos omega t plus alpha. A omega t plus alpha. A omega t plus alpha. Now again differentiating, we have d2x upon dt square is equal to minus a omega square sin omega t plus alpha, or d2x upon dt square बराबर माइनस ओमेगा स्क्वायर a sin omega t plus alpha. Therefore, d2x upon dt square plus is equal to minus omega square x, क्योंकि x is equal to a sin omega t plus alpha. So we have d2x upon dt square plus omega square x is equal to 0. This is the equation, or is this equation let this equation be true. Now comparing equation first and second, now comparing equation first and second, we have omega square. Here we see that it is also d2x upon dt square, and here also d2x upon dt square. Here is k by m, and here is omega square, and here is x, and it is x multiple of x is omega square. In this equation, first multiple of x is k by m. So we have omega square is equal to k by m, or omega is equal to under root k by m. And omega, we know that omega is equal to 2 pi by t. 2 pi by t is equal to under root k by m. Therefore t is equal to 2 pi under root m by k. Here t is known as time period of the motion. If we increase increase time t by 2 pi by 2 pi by omega, then equation A A can be written as x is equal to A sin omega into t plus 2 pi by omega plus alpha or x is equal to A sin omega t plus 2 pi plus alpha or x is equal to A sin 2 pi plus omega t plus alpha. It is your theta. Then we have x is equal to then we have x is equal to A sin omega t plus alpha. It is clear that after time t, the body repeats its motion. So after time, so it is known as time period, and t is equal to 2 pi by omega. It is given by t is equal to 2 pi under root m by k, where omega is known as angular velocity. This is all about your simple harmonic motion. Thank you.